I'm Steve Adachi from Lockheed Martin, and I'm pleased to introduce the next set of speakers. And we're going to shift gears a bit and have some talks about practical applications of quantum annealing. And our next invited speaker is Dr. John Realpe Gomez from NASA, and he's going to talk about quantum-assisted learning.
Hey, everybody. Thank you, Steve, for the introduction. Thank you very much, Professor Nishimori and all the organizers for the invitation. I'm going to talk about some work we have been doing at NASA with collaboration with Alejandro Perdomo, Marcello Benedetti, who is now a PhD student at UCL, who has been working a lot on this, and Rupa Biswas. What we have been doing is how to use quantum annealer for machine learning applications, practical applications. So we want to talk a little bit about this. So a very brief outline is what we have been doing, and essentially an introduction. Our work on training models with arbitrary pairwise connectivity, and how we use this for generating pictures, some conclusions and perspectives. So how does this work in practice for the people who are not familiar with these kind of applications, which are different from the optimization application? Essentially, you have a quantum annealer, which you can control with some parameters here. Then you run the device for the parameter that you program. You run it, you generate several samples from the device, which you can interpret as, in this example here, as a black and white picture. Each pixel corresponds to a qubit, for instance. And then you compare that with a data set that you want to, your quantum annealer to generate. So you want these samples to resemble this here. So you start comparing these guys, and with a learning rule, you start this feedback loop, and you go around it until they resemble as much as possible. After you have done that, now you want to use it. For instance, you have a picture that lacks some information, the pink here. So you can use the parameters that you learn in this process, and you can clamp instead these pixels that you know is the information that you know. This is the information you don't know. And then you clamp this pixel with large fields in the corresponding direction. And now you run the quantum annealer several times in order to have some statistics, and then you can generate samples like this. Essentially, from the sample, you can infer which is this value. So which are these pixels. So this is one application, for instance. This is what we did with the work I will describe today. So, for instance, these are some set of these are low-resolution handwritten digits, which have been optically recognized and saved, low resolution. Some of them are generated by the quantum annealer, the D-Wave 2X, and others are the real data set. Here, for instance, we have when we lack information, as the application I described before, and this is the reconstructed data set. This is another kind of data set here. We lack information, and then we reconstruct. So what I want to describe is what we have done to do this, which are the challenges to begin with for this kind of application. First of all, there is this, real quantum annealer has instance-dependent effective temperature that was described nicely in previous talks by, I think, Vinci and Mohamed Amin. So what happened is this diminished the precision, because you have to estimate this parameter if you want to go that way. There are other ways that have been explored by D-Wave recently. And this also produces a computational overhead because you have to estimate this parameter at each iteration of the process. So with the approach that we have here, we only have visible variables as I described, so we don't need to estimate that temperature. The connectivity of the state-of-the-art hardware is sparse, as you know very well. So this, in machine learning application, this makes difficult or perhaps impossible to capture non-trivial correlations in real data sets. And so using the native topology. So we use embedding techniques like in the two talks before about to produce a arbitrary pairwise interaction. And then we still have the parameter setting problem, which is how to optimally pick the value of those additional parameters. We learn those parameters too using data. So also the parameters are noisy, which can lead to problem misspecifications and poor performance. As we are learning the parameters from data, we expect, I mean, the learning rule essentially is try to minimize the errors or the statistical errors in the sample generated by the annealer in order for them to resemble the dataset. So in that sense, we still think this, in this approach, you can handle better this noisy parameter that you can have. And I discuss a little bit more about that later. And there is also this challenge here, which I think is a hard challenge, how to properly benchmark quantum annealers in sampling applications. I think optimization is already difficult. In sampling is, I think, much harder. So this framework that I describe here is suitable for benchmarking in that it essentially takes away most of the complexity in machine learning, and essentially the complexity now here remains essentially concentrated on sampling. So that's, I think, an ideal setup for benchmarking. But there are several challenges that need to be tackled to do this in a way that's sort of satisfy the scientific community. So I describe here briefly, more or less, what in few words, part of what Mohammed Hamid said yesterday. This is essentially based on a work by him. You have the annealing Hamiltonian of with standard transfer field, and under certain conditions, not always, under certain special conditions, the states, the distribution of samples produced by the annealer can be described by a Gibbs distribution of a Hamiltonian at the freezing point. So this is the working assumption for us, essentially. We assume, this is working assumption, we assume that the quantum annealer is actually sampling from this kind of density matrix at a constant transfer field, which can be 0 or not, can be small, we don't know. But with this working assumption, we can derive the learning rule that allows us to train this device. But I want to stress that when we started this work, our working assumption was that the distribution was a classical Boltzmann distribution. Still, we have the intuition, as I will describe later, we have the intuition that this could still handle quantum corrections. And also, and then this was proved recently by some guys from Microsoft that indeed this is the learning rule that I present here. Is based on their work. It's actually trained these more general quantum models. So exactly. So we still think this can handle non-equilibrium deviations for using the same intuition, but we don't know a proof for that. So we think this is our working assumption, and we run experiments, we see it works. Still, we believe this can be more general. This assumption could be relaxed, but this is another assumption. Okay, this is what we think from the experience. So the idea is then this is this is essentially this quantum model were investigated first by Mohamed Amin, using some approximated techniques to handle that. But in the case when we have, the case we deal with here, which has no hidden variables, this can be derived exactly as it was done by Keferova and Wipp, using the relative entropy, quantum relative entropy, where you have the density matrix describes in the diagonal, it's a diagonal matrix, which in the diagonal is encoding just the empirical distribution of data. And this is the model that I described previously. And so we want to minimize this distance. And then we use the gradient descent method. So we just update the parameters following the gradient, and the gradient has exactly this form, exactly. So the assumption here is the constant transverse field. So we are forgetting about that. So we just need to derive J and H over J and H. This is the learning rate. And one of the complexities, I think, in benchmarking devices, because you have so many degrees of freedom that you can think this learning rate could be a constant, could vary, could be a whole path that you have to optimize. So there are many possibilities. Okay, so when these two terms here of the annealing schedule satisfy this condition at the freezing point, then this essentially leads to a classical Boltzmann distribution. I had this described in previous talks. So this could be the case in our experiments. We don't know. But what I want to stress is that the learning rule with which we train the quantum annealer is general, more general than classical Boltzmann machines. Okay, so one reason why we think initially we were working with the assumption of classical Boltzmann distribution, but what was the idea of gradient descent? That you estimate the gradient and you follow the direction of the gradient, but you can have deviations of the gradient, and as long as the projection of that gradient on the true gradient is positive, you are still moving in the right direction. Even if you can go like zigzagging, for instance. Even if the true gradient goes like that. And this is also what happened in classical machine learning, because you cannot compute the exact gradient. You can estimate it. You can get a noisy estimate of the gradient. And so you are zigzagging somehow. But so that's why we thought we can also handle quantum corrections. As I say now, this is proof, correct, but exact, by these people from Microsoft. Still, we think that it can also handle some deviations from non-equilibrium deviations. So, okay. Now, one of the limitations of limited connectivity, so we do this standard embedding approach, which you can think of like you have the original data set, and you map that data set to a larger data set, because you need to replicate. If you were to work with this data set here with a classical model, you can do it, for instance, with only one variable per pixel if they are images, and and that's it. But so you can have the number of logical variables could be equal to the number of pixels that you have in the data set. But here, because of the sparse connectivity, what we do is we map this data set into a expanded data set. We have redundancy. And now the question is, after that, then we can train the annealer here. So we are essentially, for instance, in some of the experiments we have data set here with about 40 variables, the original data set. So images, we are about 40 pixels. But when we come here, we have a data set with over 900 qubits. And when we train the device, at the beginning, the device doesn't know about the data. Only at the end, it has acquired enough information about what is the structure on the data set. But during the training, we are training a quantum annealer with over 900 qubits. So these are experiments that are working with that assumption, and the results suggest it's working well with over 900 qubits. Because this is one of the questions that is around also, whether you have a large system, these assumptions work or not, because maybe the system does not normalize, but as I said, it may be that they handle also non-equilibrium deviations. So, okay. So now you are in this extended, you have a larger data set, a data set with larger resolution, and now we work with the assumption that we said that gives distribution. We have to do this embedding them. Now, even if, for instance, this triangle, if we want to embed it in the chimera graph of the D-Wave machine, we have to do something like this, for instance, and we need this additional parameter. And one of the problems in optimization, for instance, is how to set the value of this additional parameter in such that you have optimal performance. So this is the parameter setting problem. In optimization, for instance, best performance could be highest probability of finding the ground state. The work by colleagues in our team, for instance, in this paper here, PRX, and this other by Alejandro. Well, this PRX has, for instance, the following intuition. For having optimal performance, the parameters of the problem and the parameters, additional parameters of the embedding, which in that case are chains, ferromagnetic chains, and the problem is a spin glass, a Sherrington-Kirkpatrick model. So the intuition is that both systems, the chains, the ferromagnetic chains, and the rest of the model should cross the quantum phase transition at the same time, more or less. That's intuition. So you have the critical point for ferromagnetic chains are order of the coupling of them, and for the spin glass is order square root of n and the typical value of the parameters. So this suggests that for optimal performance, the two guys, the typical values of the spin glass and the ferromagnetic coupling, they should be somehow proportional. But in optimization problem, these values are fixed. You fix them, you have a problem, you fix them, and you run the device several times. In machine learning, these guys vary dynamically. So you have to adjust these guys during the learning. You will have a fixed set of parameters. And so, but still, we have this relationship. So we expect they have to grow together. So we have the learning rule that we mentioned before. We have, as usually done in machine learning, we have some additional parameters for regularization and momentum in some cases. So we try to avoid them as much as possible, not to have more complexity in the experiments. But okay, so we learn also these parameters. We let the whole device learn from data. We just transform the original data set into an expanded, higher resolution data set where we have redundancy, and now we train the whole network on that data set, the whole quantum annealer. So, for instance, we can think of, we train an Ising model, a classical Ising model, 15 variables just to be able to compute exactly, quickly the statistics of this. We generate a data set exactly with exact sampling, and now we train the quantum annealer to generate this. This has, I think, 15 variables. It has 76 qubits. And after it's trained, then now we can use it to generate samples, and we have to transform it back into the original data set. And we can now, because we know this model, we can use a proxy, because another difficulty in machine learning is that how do you evaluate performance, because it's already hard to compute. For instance, the likelihood function, which allows us, or the KL divergence, is hard to compute. So how do you evaluate it this is a standard problem also in classical machine learning. How do you evaluate generative models in an efficient way? Okay, so we have this proxy here because we know the model, so we know the probability distribution, and we can compute this. And the model is small, so we can compute this. So by doing this, now we have, this is our proxy. The value the value to be reached is this green horizontal line here. because we know the true model, so this is the value that should be reached. And now we have, for instance, is the training set, and now we have, for instance, the blue line is exact, is doing exact sample, is learning with using exact sampling from the classical model, using classical algorithm. And we have this growth here, and we have this fixed learning rate. And now we have the quantum annealer with the same fixed learning rate, which is these circles here, which we see it grows faster in the beginning, and it essentially grows faster. Okay, there could be many reasons for this. As I say, there could be the effective temperature, essentially, that we are not estimating, but the effective temperature affects the learning rate, so the learning rate effectively varies in a way that we don't know. The quantum annealing, because it's endogenous, or it's intrinsic of the quantum annealer, this variation. It depends on the instance. And we are not estimating the temperature. I think there are now techniques, maybe Jack will speak about that, how to have a good estimation of the temperature. Okay, we are not estimating. But we have a completely varying learning rate. It's a possibility. We don't know how it varies. There are infinite possibilities it can vary. So then, should we start varying the learning rate in the classical algorithm? How should we vary? Maybe the best way would be to estimate temperature, so we know very precisely, so we know the learning rate at each iteration, and then we use the exact same learning rate for the classical algorithm. That's a possibility. Or should we use the standard varying of learning rate as in classical machine learning, or should we use the whole infinite space of paths? So that's always a question in this thing. So now, varying the learning rate, the constant learning rate here, we see that the classical algorithm using exact sampling performs better than the quantum annealer here. So this gives some indication that the varying effective learning, the varying effective temperature or varying effective learning rate could be playing a role, but this is not a conclusive answer. Now, again, but we use the same fixed learning rate now for the quantum annealer. And again, the quantum annealer goes faster in the beginning. Okay, so now there was a question about because when we expand the data set to a higher resolution and we go to the space of the quantum annealer, which have more parameters, and more parameters than the classical model, if you are going to use a classical model. So the question is this expanded parameter space helping quantum annealing? And the answer is not. We have here showing that if we do the learning, because here we are using now okay, sorry. This is the classical model, exact, on the small classical model, 15 variables, and this is the expanded. This is what we are working on, the expanded with 76 variables, but now using simulated annealing because we cannot handle this exactly. And we see that we try the simulated annealing, we make it as slow as necessary, such that we find essentially a saturation in the performance. This didn't increase more. We use this schedule here, but if we increase more these values, the number of Monte Carlo steps, this didn't grow more. So we stop there, and we see that there is not an advantage due to that, to the additional parameters, or when you move to the space of the quantum annealer. So now we have this application to digits, the low resolution digits I mentioned before. So we have this. We have this in the number of pixels, 42 pixels. We map here into the quantum device, and we have the picture that I mentioned before. So these are generated by the quantum annealer, and these are the original data set. These were never seen by the machine during training, so this is completely new data for them. Okay, so now we come back just as a side remark, come back to the idea of the parameter setting problem. These two guys should grow together in a way that is not obvious, because this looks like a linear relationship, because n looks like a constant, but this is true because, in this case, it's true because in the work, in this work, the model was fixed, was a Sherrington-Kirkpatrick model, is fixed, and so you know that it will work. This is the critical value, the critical transfer field goes like that. However, in machine learning, even if I start with a fully connected topology, the final solution might be a chain. I don't know. And so actually, I don't know. So this factor here plays also a role. So it's not just a linear relationship. It could be, or maybe not. So this is a very preliminary data because we haven't looked at this before. These are sent by Marcello yesterday. And essentially, we see here for the three data sets that we have studied, how the ferrocouplings grow and how the other parameters grow. This is the standard deviation also. In the three cases, we see a similar performance. And the typical value, when you have this order system, the typical value is given more by the standard deviation than by the mean. In this case, all the means are essentially 0. So as typical value, we are using the standard deviation, and we compare with the ferrocouplings. And for instance, here this is a correlation plot. We have essentially a linear, this is the initial point with 0, 0. But then we have essentially like, it looks like a linear relationship. Also, this is for the Ising model, and also for the digits and the bars and stripes also looks like linear relationships. However, there's some nonlinearities. But if we look at the ratio of these two guys during the learning, we see that initially they grow together, but then it sort of saturates. So up to here, we have checked that none of the parameters has gone out of range. Not one parameter has been out of range. And so we see that essentially it's like, even though the learning rules say that the ferromagnetic couplings should grow forever, the rate at which they grow decreases when the errors start decreasing. And at some point, this is like the standard experiment we do in undergrad of a discharge of a capacitor. That is like the model is exponential decay that never goes to 0, but at some point for practical purpose, you stop. Something similar could happen here when the ferro should always grow, but at some point it starts growing so slow that for practical purpose it doesn't matter. And this is, we see here, it's sort of saturating the growth of the ferrocouplings start going slower than the typical value of the problem parameters. So in this case, we see that it's indeed a decay. But in this case, we have regularization, which is a standard technique in machine learning to try to have better models, to learn better models. So you try to penalize high values of the parameters. In this case, we penalize everything, including the ferrocouplings, and that could be one reason why it now decays. So we think this can be also of use in the future for optimization problems. For instance, we can think of a sort of annealing, of a simulated annealing of a quantum device where you start with scaling these parameters scaling up until you reach some value, for instance, and you can do the search of the optimum. And that's a possibility, and then you can also use the data that you are generating on the way to estimate, for instance, an optimal parameter setting for optimization problems. That's just an idea we haven't tested. So I don't know how much time I have. This was like an optional slide. 10 minutes, okay. Okay, so let me tell a few remarks. As I say, okay, I already mentioned this. The model is determined, essentially, in the case of the classical model, is determined. I mean, a probability distribution, like a Boltzmann distribution, is determined by this fact, but not by the parameters alone, but a product with the temperature. And so, this the fact that the distribution depends on the product will translate later in that it will vary, the learning rate will be multiplied by the temperature, and this is why it also varies. So, as I say, the couplings, ferromagnetic couplings, grow in this way. So it depends on what are the errors. This is essentially which are the errors made, because these two variables, these two qubits, are supposed to represent the same variable. They are supposed to represent the exact same variable, and so if you compute the correlation, it should be 1. But it's not, when you run the experiments, it's not. For this to be true, you need to go to, in theory, you need to go to infinite value. And this is why the learning root is giving you this value, this grow, which is always grow, okay? But the rate of growth can decrease. Furthermore, when you have regularization, this counteracts the growth. Okay, as I said, the true gradient, when you are doing machine learning, you are trying to follow the gradient of the function that you are optimizing, the likelihood function or the relative entropy or the KL divergence, whatever you are using, you are trying to follow the gradient, but as long as you have an approximated gradient that still projects positively on the true gradient, you are still moving in the right direction. This is, but if this is a sort of random error, it shouldn't matter. If it's a systematic error, at some point it should matter, but, okay. Now, there is something interesting here about also error correction. For instance, a possibility for error correction in machine learning, which is using ideas from what is called black box machine learning with black box models. So no models, black box devices, samplers. And the idea, one of the standard ideas in black box machine learning is that since you don't have a model, but you want to estimate where to move the parameters, the control parameters of that black box, one idea is you generate samples, you move the parameters, which is similar to Monte Carlo, you change the parameters, you pick a random direction in the space of the control parameters. You pick a random direction, and now you move in that direction, and you evaluate a proxy of the learning. For instance, the ideal case in here would be the likelihood, but that's hard to compute. But let's say the likelihood, you move in that direction, you evaluate the likelihood, and now you go in the opposite direction, and you evaluate the likelihood, and you move in the direction on which you have a better value. And then you pick another random direction, and you move, you compare with the two directions, and this is the idea. So we can think of combining these ideas. For instance, we have model-based machine learning, but rather than picking a direction totally at random, we can pick a direction given by the gradient computed in this way, based on a model based on a Gibbs distribution. You pick the gradient, and now you move in that direction, and then in principle, if you were able to compute the likelihood, you can see whether that's the right direction, or maybe you better move in the opposite direction, and that would be a way of error correction. What's the challenge? One of the challenges here is a proxy that is efficient to compute, because the likelihood is not efficient to compute. So what is the proxy that you can use for implementing efficiently that kind of, let me call it error correction, in this application? And okay, now there is, the idea is in more general models. I think the quantum Boltzmann machine that Mohamed Amin studied, and also the standard techniques, for instance, the deep Boltzmann machines in deep learning, they require hidden variables. When we have hidden variables, then this nice feature that we can forget about temperature doesn't work. There are alternatives that I know Dewey is trying, which is very interesting. So, but when we don't have hidden variables, we don't know, this part here of the learning is correlations of the data and correlations of the model. But when we have hidden variables, these correlations actually depend on the model also, on the data and the model. And so you need to, is what makes difficult you cannot work all in the quantum annealer. You also have to work a bit on the standard computer. But when you don't have hidden variables, this term depends only on the data. It becomes a constant, so you can forget about estimating the model part here. It's just a constant, so you can forget about that. So to sort of conclude here, so we have been working with this to try to understand better, and we have been working like trying to, from the bottom up, understanding the difficulties and also in the application domain, and experimented with this. So we have this arbitrary pairwise connectivity when we learn also the parameters, and this allows us to work without estimating temperature, which could be a noisy estimate also, and it needs a computational overhead. Okay, so we can handle that. We generated it. Now there's a lot of work on that. There's, I saw a lot of nice poster here. We had generated this last year, like one of the largest data sets, larger resolution data set with quantum annealers. And I think what I think is suitable framework for benchmarking. I think this is the first kind of approach I would try for benchmarking. I know the people from D-Way are also doing some work on benchmarking well-known machines, which is very interesting. Still, as I think there is a lot of challenges to really do this in a way that satisfy the scientific community in general, because you want to go large, for instance, but if you go large, how do you, for instance, suppose that you want to reach a target Gibbs distribution, say of 500 or 1,000, now we have 2,000 qubits, so of 2,000 variables. You want to reach a target Gibbs distribution of 2,000 variables. How do you evaluate, to begin, how do you evaluate that Gibbs distribution? Just to compare. How do you evaluate that? Just to compare. So you have to rely on approximation method. You have to run approximated algorithms, classical or quantum-based, to reach that thermal state. But if the problem is hard, that's already hard. How do you do that? In a way, let's say, in a way that is conclusive. That you can, because then you can blame the classical algorithm didn't thermalize well the Gibbs distribution you wanted to compare to. Or maybe you can think of planting solutions. So the idea of planting solutions in optimization problems here it can be generalized to planting sets, samples. So I know there is some work on that in the spin class community. But as far as if I remember well, it's not easy to prepare hard problems that way. So, but maybe Jack is more acquainted with this, I don't know. But I remember some papers on that. There is, as I say, all these hyperparameters that you have to optimize. How do you do that? We have to optimize also the annealing time. And for one run, for instance, in this simple system that we study, for instance, here, we have only 500 iterations. In the other data set, we have around 3,000 iterations to reach something decent. Per each iteration, this is the smallest system we have studied. Per each iteration, we need about 200 samples. This is what we use to have some decent results. So here you have about 100,000 rounds of D-wave for one single instance without any statistics. Zero statistics, just 1 point. When in optimization you have one instance, you run, let's say, 100,000 runs to have some statistics on that single instance. Yeah, or any other number. Here, just one single run of learning is hard. If you want, one ideal situation is fix 1 point and just do sampling. But you don't know which is the distribution that D-Wave is sampling from, in the D-Wave in this case, or a quantum annealer. because you don't know which was the freezing point. So you don't know what is the distribution. So you need to learn that. So there's a lot of complexity that we have been working on. Maybe let me just give 2 ads for people who are interested in research opportunity programming using the D-Way device and NASA. You can contact Davide Venturelli to talk about this. And we have also research opportunities at NASA for working on quantum machine learning. Could be interns, postdocs, research scientists. Please contact Eleanor Riffel or Alejandro Perdomo Ortiz. And thank you very much.
Okay. Thank you, John. So while our next speaker gets ready, I think we have time for some quick questions.
It's very confusing.
So you mentioned this black box learning, but you also said that the likelihood is not efficiently computable. So then what? Do you know? You have any ideas about how to do that?
Yeah,
how to use black box learning?
Yeah, you can, for instance, use. You have to sacrifice quality in order of efficiency. So you can, instead of using the likelihood, you can use some other error function, for instance, reconstruction error. You sample and you compare with the data set and you sort of compute the statistical error being done. And this gives you a proxy of whether you are moving in the right direction or not. But you have to sacrifice accuracy to do this.
Okay. Yeah, but if you minimize the reconstruction error, I guess you are not doing Boltzmann machines anymore, right?
Yeah,
you're
that's
using other models. I would say
that's
autoencoders or things like that.
That's no, but what I say is in the standard approach of black box machine learning, you pick a direction at random in the space of control parameters. You pick a direction at random. And now you move in that direction or in the opposite direction, depending on the evaluation of this function, or the error function. Yeah? What I say is here you can, instead of picking at random, which is, it's hard to pick a good direction at random in this large space. So rather than picking at random, you can use the Boltzmann machine learning approach to estimate the gradient. So you pick the gradient. And now, you move in that direction, which is likely correct, but when it's not correct, you move in the opposite direction. Now, I agree. You have to estimate the likelihood, then this will be hard. That's what I say. That the challenge is how to find a good proxy for doing this efficiently. I'm just telling you one possibility, but I'm not saying this is the right way to go. But one possibility is reconstruction error. So you pick the Boltzmann gradient, not random, Boltzmann, and you move. And now you evaluate this proxy to see whether it was a good move from the perspective of reconstruction error or not, for instance.
Okay. Any other questions? Okay, let's thank our speaker again.
Thank you.